Hello and thank you for joining us. My name is Daryl and I'm joined by my partner Charles, and this is the presentation of our submission for Homework 1 for MECH 6333 of the internal pressure of a beverage container. To create our beverage container part, we used a revolution of this sketch to create a shell. The dimensions for this shell were determined by measurement of a soda can. And we created this part as a result. The material used for our aluminum was aluminum 3104 H19, which a Google search told us was a common species of aluminum used in the creation of soda cans. The properties of that are density of 2,720 kilograms per cubic meter, with a Young's modulus of 69 gigapascals and Poisson's ratio of 0.34. The material was assigned by creating a section, selecting the material. Additionally, because it was a shell that we used and not a typical revolve, this is where we assigned a value for the thickness, and 9.7 times 10 to the negative fourth meters was another value that was provided to us through a Google search. To mesh our part, an instance was first created within the assembly, and then the part was seeded. In order to create the most elements possible while staying with under 1,000 for the student version, we came here and used the seed part instance tool to adjust the approximate global size, ending here on this number of 0.00555, which provided us with 977 elements for our mesh. The mesh was then generated using the mesh part instance tool, resulting in the mesh that you can see here.
Now, for our boundary conditions, we felt that fixing the base of the can would lead to lower stresses than would actually occur because it would be supported by the floor. Now, under this mindset, it became more reasonable not to set boundary conditions, especially since the weight of the can causes forces of negligible scale when compared to the forces we would observe from the internal pressure. So a load of 250,000 was selected for uniform pressure, which we entered, and abaqus asks you which side, the brown side or the blue side. Since we know our outside is the blue side, then we apply it on the brown side. This applies the uniform pressure on the inside surface of the can. We used a ratio of the equation PV equals MRT to calculate the new pressure of our can of air. Within the ratio, the volume, mass, and gas constant remain the same, so they are canceled out, while the pressure and temperature become proportionally related. Now, from our new expression and inputting the initial temperature and pressure with the new temperature, the new pressure is calculated at 275.6 kilopascals. Here we're going to go over some of our contour plots. Now, for aluminum at the initial 250 kilopascals, you've got a few of these. Now, at the higher pressure, you have these. Now, for polycarbonate at the lower internal pressure, polycarbonate at the higher internal pressure, aluminum oxide at the lower internal pressure, and aluminum oxide at the higher internal pressure. Here is a more easily understood comparison of our results. You can see that the von Mises stress, max principal stresses, and max principal strains were consistently higher for the higher pressure case. This was an expected result, though there is one outlier. After multiple simulation runs, this seems to be an issue attributable to floating point errors from the small numbers or meshing irregularity from the coarseness of the mesh. The aluminum represents a higher von Mises stress than the others, but presented much less principal strain. Polycarbonate presented less stress, but significantly more strain than the other materials. Aluminum oxide presented middle von Mises stress, but far less strain than the other materials. The overall maximum principal stresses hover near similar values with a notable increase upon the increase in internal pressure. This concludes our exposition of Homework 1. Thank you for watching and feel free to ask questions in the comments.